In the quiet groves of ancient Greece, long before telescopes pierced the heavens or laboratories hummed with electric coils, humanity first tried to make sense of the miracle that allowed us to see the world at all light. Among the earliest and most enduring ideas about its nature was one, so strange to our modern ears that it almost sounds like magic. The Greeks, those restless questioners of everything under the sun, widely believed that light did not come from the sun, from fire, or from objects themselves. Instead, they imagined that light streamed outward from the human eye like invisible feelers reaching into the darkness to touch the things around us. Only when those feelers made contact could we perceive shape, color, and distance. In other words, seeing was an active process. The eye was not a passive receiver but a kind of lantern projecting rays into the world. This idea, today called the emission theory or extramission theory, was not the wild fancy of a single dreamer. It was taught, refined, and defended for nearly 1,000 years by some of the greatest minds the ancient world ever produced. Empedocles, the Sicilian philosopher who lived around 490 BCE, pictured the eye as a lantern inside the head. Within the pupil burned a sacred fire, a gentle flame sent by the goddess Aphrodite herself. That inner fire reached outward through the eyes in straight, delicate rays mingling with sunlight during the day, so that the two lights could meet and allow vision. At night, when sunlight withdrew, the eye's own fire still wandered out, though weakly, which is why we see less clearly in darkness. Empedocles even tried to explain color. Different objects altered the quality of the fire rays that touched them, and the altered rays returned to the eye, carrying information about red, blue, green. A century later, the mathematicians of Athens sharpened the idea into something almost geometric. Euclid, the father of geometry, wrote an entire treatise called Optics around 300 BCE. In it he treated sight rays as perfectly straight lines, shooting from the eye in all directions, forming a cone with its tip at the pupil. Anything lying inside that cone of rays could be seen. Anything outside remained invisible. Euclid used this model to explain perspective. Objects farther away appear smaller because fewer rays from the eye strike them. He even gave rules for how mirrors work. When a sight ray hits a polished surface, it bounces back at an equal angle, exactly the same law of reflection we teach today, though in reverse direction. To Euclid, reflection happened not because light was coming from the object and bouncing into the eye, but because the eye's own ray struck the mirror and returned to its source. Plato, in his dialogue Timaeus, described vision as a merging of three fires: the pure fire inside the eye, the fire of daylight filling the air, and the fire streaming from visible objects. When all three met in harmony, smooth and gentle, we saw clearly. If the fires were too violent or mismatched, pain or blindness resulted. Even the great Ptolemy of Alexandria, in the 2nd century CE, wrote a 5-book Optics that built on Euclid. He measured angles of refraction, how sight rays bent when passing from air into water, glass, and compiled tables, all while assuming the rays originated in the observer's eye. Why did this idea feel so natural for so long? Think about the lived experience of seeing. When you open your eyes in a dark room and suddenly perceive everything around you, it feels as though something has gone out from you into the space. When you stare intently at someone across the room, it feels as though your gaze is touching them. Many languages still preserve this sensation when we say, "I threw him a glance," or "her eyes pierced me." Small children often cover their own eyes to hide, believing that if they cannot see others cannot see them, an intuition perfectly compatible with the idea that vision requires active probing rather than passive reception. Even the act of pointing at something while saying, "Look," suggests we are directing an invisible beam. The emission theory also solved certain puzzles elegantly. It explained why we see stars only at night. During the day, the sun's overpowering light drowns out the weak rays from distant stars sent toward Earth. No, wait, the Greeks reversed it. During the day, the sun's light interfered with our eye rays traveling all the way to the stars and back. At night, with less interference, the rays reach the stars and return carrying their faint gleam. Mirrors worked because the eye ray, striking the polished surface, rebounded directly into the same eye, creating the illusion of another person standing behind the glass. For centuries, almost no one challenged the core assumption. Aristotle, who disagreed with many things, accepted that something left the eye, though he thought It was not fire but a kind of motion transmitted through the transparent medium of air. Hero of Alexandria used the emission model to prove that light or sight rays always take the shortest path, deriving the law of reflection centuries before Ibn al-Haytham. Even the early Christian thinkers, when they discussed the evil eye, imagined harmful rays shooting from envious glances to injure the victim. Yet cracks began to appear, small at first. If rays truly stream from the eye, why do we not see in perfect darkness? Why does closing one eye not reduce the brightness of the world by half? Why can a tiny firefly be seen from far away, but our own powerful eye fire cannot illuminate a dark room? These questions were raised occasionally, but the authority of Euclid and Ptolemy was so great that the theory endured. Then, in the golden age of Islamic science, a lone voice rose to demolish the entire edifice. Around the year 1000 CE, in Basra and later in Cairo, Abu Ali al-Hasan ibn al-Haytham, known in the West as Al-Hazan, wrote his monumental book of Optics. He began with a simple but devastating experiment. He sat in a completely dark room and had an assistant light a candle outside the door. The moment the door opened, light flooded in and Al-Hazan could see the flame. Even though his eyes had sent no rays outward into the darkness, the light had come to him. He repeated the demonstration with sunlight entering through a pinhole, forming an inverted image on the opposite wall, proof that light traveled in straight lines from objects to the eye, not the other way around. Al-Hazan went further. He showed that when we look at the sun, our eyes hurt because something powerful is entering them, not leaving them. He dissected eyes of animals and studied the lens and retina, proposing that vision occurs when light rays from each point on an object converge to a corresponding point on the back of the eye, forming an upside-down image that the soul then interprets. For the first time, vision was passive reception, not active projection. Though Al-Hazan's work spread slowly first in the Arabic world, then translated into Latin. In the 13th century, the old emission theory lingered in Europe like a ghost. University lecturers still taught Euclid. Painters and architects still used perspective rules derived from sight ray cones. Even Leonardo da Vinci, centuries later, occasionally slipped and spoke of visual rays leaving the eye, though he also drew accurate diagrams of light entering the pupil. But the spell was breaking. Once people began measuring the speed of light in the 17th century, first Ulrimer in 1676, then James Bradley and others, it became impossible to sustain the ancient picture. If light had a finite speed, and if it took 8 minutes to reach us from the sun, then when we look at a sunset, we are seeing light that left the sun long before our eyes opened. The rays could not possibly have originated in our pupils. They were ancient travelers arriving from 93 million miles away. Thus the emission theory, which had reigned for 2 millennia, finally collapsed. Yet its long dominion tells us something profound about how science works. Ideas can feel completely obvious, perfectly intuitive, backed by the greatest authorities, and still be utterly wrong. The Greeks were not stupid. They were prisoners of everyday sensation and a lack of decisive experiments. Only when someone like Al-Hazan dared to sit in absolute darkness and wait for light to come to him did the truth reveal itself. Today, when we switch on a flashlight and watch the beam cut through fog, we are unconsciously performing the experiment that killed the ancient theory. The light goes out from the source, not from our eyes. And yet, in a strange way, the old Greeks still speak through our language. We still talk about casting a glance, shooting someone a look, or feeling that a stare burns into our back. The ghost of emission theory lingers in metaphor, long after it vanished from laboratories. So, the next time you open your eyes at dawn, and the world floods in without any effort on your part, remember the thousands of years when the greatest minds believed the exact opposite. Remember that seeing, the most immediate of all human experiences, was once imagined as the eye reaching out to embrace the universe, rather than the universe reaching in to embrace the eye. That long, beautiful mistake is the true beginning of the story of light before waves, before particles, before quanta, a story that started not in the stars but inside the human soul, project its fire into the waiting dark. And yet, even as Al-Hazan's quiet revolution began to seep westward through dusty Latin translations, the old intuition refused to die completely. By the time Europe awoke from its long medieval slumber, the question of light had become urgent again, not just for philosophers in candlelit libraries, but for painters, architects, gunners, and sailors who needed to understand lenses, mirrors, perspective, and the horizon. When the 17th century arrived, the stage was set for a battle that would eclipse every previous debate, a duel between two of the greatest intellects the world has ever known, fought not with swords but with prisms, mathematics, and merciless logic. On one side stood the towering figure of Sir Isaac Newton, alchemist, theologian, master of the Royal Mint, and the man who had tamed gravity itself. On the other, a quieter, almost forgotten Dutchman named Christian Huygens, a clockmaker, son who built the finest telescopes of his age and discovered the rings of Saturn. Between them lay the entire future of physics, and the weapon they chose was light itself. Newton did not merely prefer the idea, he declared war on every alternative. In 1672, at the astonishing age of 29, he sent a short paper to the Royal Society in London titled A New Theory About Light and Colors. It was only a few pages long, but it exploded like a grenade. Newton described how he had darkened his chambers at Trinity College, Cambridge, bored a tiny hole in the window shutter, and allowed a single beam of sunlight to enter. He placed a glass prism in its path, and watched, spellbound, as the white beam shattered into a silent rainbow. On the far wall, red, orange, yellow, green, blue, indigo, violet stretched out over 5 feet long. To Newton this was decisive proof. White light was not pure or simple, as the ancients and even Descartes had thought. White light was a mixture, a chaos of different colors, each with its own degree of refrangibility, its own stubborn tendency to bend, when passing from air into glass. Red bent the least, violet the most, and crucially, once separated, each color could never be changed into another. You could send the red beam through 100 more prisms, and it would always remain red. Therefore, Newton concluded, light must consist of tiny material particles, corpuscles, each corpuscle carrying its own unchangeable size or shape that determined how much it would bend. He pictured these corpuscles streaming from the sun in straight lines at unimaginable speed, bouncing off mirrors like perfect billiard balls, slipping between the particles of transparent matter with greater or lesser ease. When they moved faster in glass than in air, a prediction that turned out to be wrong, but no one knew that yet, and they explained why a prism separated colors, larger corpuscles, red, were less deflected by the dense medium, smaller ones, violet, were shoved aside more sharply. Reflection, refraction, even the strange new phenomenon of Newton's rings, those delicate colored circles, seen when a lens rests on a flat sheet of glass, all fell into place under the corpuscular spell. Newton was not content with mere explanation. He performed experiment after experiment designed to leave no escape for rival theories. He showed that if you isolated a single color from the first prism and sent it through a second, it did not split further. He built a crucial experiment with 2 prisms and a board with a hole in it, proving that color was an original property, not created by the glass. He even mixed the rainbow back together again, using a lens and a second prism, recovering pure, white sunlight. The message was unmistakable. Light is made of particles, and anyone who disagreed was simply not looking carefully enough. Across the English Channel, Christian Huygens read Newton's paper with growing unease. Huygens was no stranger to light. As a young man, he had ground lenses so perfect that he discovered Saturn's largest moon, Titan, and resolved the planet's mysterious handles into elegant rings. He had spent years thinking about how light propagated across the vast emptiness between stars. To him, Newton's corpuscles felt like a step backward into the crude atomism of the ancients. Where was the beauty, the unity, the mathematics? In 1678, Huygens presented his own treatise to the Paris Academy of Sciences. He called it Traité de la Lumière. In it, he proposed something breathtakingly modern. Light is not a stream of bullets, but a wave, an undulation spreading through an invisible, all-pervading medium he called the ether. Imagine, he said, dropping a pebble into a pond. A pulse spreads outward in perfect circles, yet the water itself does not travel with the wave, only the disturbance moves. In the same way, luminous bodies vibrate, sending wave pulses through the ether. Those pulses reach our eyes without any material substance crossing the distance. To explain how waves could travel in straight lines instead of spreading sideways, like sound, Huygens invented a principle that still bears his name. Every point on a wavefront, he said, acts as a new source of secondary wavelets. Where these wavelets reinforce one another, light continues forward. Where they cancel, darkness reigns. With this single idea, he could derive the laws of reflection and refraction geometrically, without invoking mysterious forces acting on particles. He even explained double refraction in Iceland's spora crystal that split a single beam into two, something Newton's theory struggled with painfully. For a few brief years, it looked as though the debate might remain civilized. Newton himself, in his great 1704 book Optics, published in English rather than Latin so that everyone could read it, included a series of polite queries at the end where he wondered aloud whether light might not sometimes behave as if it had a wave-like aspect, but beneath the courtesy burned absolute certainty. Newton used his immense authority, president of the Royal Society, national hero after the Principia, to quietly suppress wave ideas in Britain. When a Scottish mathematician named Thomas Young later dared to revive Huygens' views, Newton's disciples ridiculed him so fiercely that Young abandoned physics for Egyptian hieroglyphs. And so, for nearly the entire 18th century, the corpuscular theory reigned supreme. Textbooks taught it. Optical instruments were designed with it in mind. Painters spoke of rays shooting from objects exactly as Newton described. The ether was dismissed as an unnecessary fantasy. After all, if light was made of particles, it needed no medium, just as a cannonball needs no invisible jelly to fly through the air. Yet the victory was hollow. Newton's theory, for all its intuitive appeal, rested on one fatal prediction: light should travel faster in water than in air, because corpuscles would be sped up when entering a denser medium, just as a comet speeds up falling toward the sun. In 1850, 53 years after Newton's death, Léon Foucault and Hippolyte Fizeau finally measured the speed of light in water with exquisite precision. The result was devastating. Light slows down in water. Newton's beautiful edifice cracked from top to bottom. The corpuscular theory did not collapse overnight. Old men who had built their careers on Newton fought bitterly, but the new generation, young Fresnel, Arago, saw the truth clearly. Light bends toward the normal when entering water because the wavefront slows on that side. First, exactly as a line of soldiers marching from pavement onto mud would wheel around, the wave theory, buried for a century, rose from its grave with irresistible force. Thus ended the second great chapter in the pre-quantum story of light. From the eyes imagined fire rays of the Greeks to Newton's triumphant corpuscles, humanity had spent 2,000 years believing that light was something shot outward first from the observer, then from the source. Only in the 19th century did we finally accept what Alhazen had glimpsed a millennium early. Light is a disturbance traveling toward us, not because we reach for it, not because tiny bullets are fired at us, but because the entire universe is gently shivering with invisible waves that carry the sun's fire across 93 million miles of emptiness directly into our waiting eyes. The irony is exquisite. Newton, the supreme genius of mechanism, had revived the most ancient of intuitions that light is made of projectile particles only to be overturned by measurements he himself had made possible. And Huygens, the quiet clockmaker who believed in harmony and undulation, had spoken the deeper truth without realizing how vast its consequences would become. When Max Planck stood before the German Physical Society on the cold evening of December 14, 1900, and reluctantly proposed that energy itself might come in tiny indivisible packets, he little suspected that he was reconciling the irreconcilable, that light would prove to be both wave and particle at once. But that final twist belongs to another story. For now, let us simply marvel at the centuries of human striving, from Greek fire rays to Newtonian corpuscles, that were necessary before we could even frame the right question. The history of light before Planck is not a tale of steady progress toward truth. It is a story of magnificent wrong turns, of beautiful ideas that grip entire civilizations for lifetimes, only to dissolve like mist at dawn. And in that long wandering we see something deeply human, our stubborn need to touch the world, to cast our gaze outward, and believe that the light begins with us, even when every star in the sky is patiently teaching the opposite lesson. The year is 1672. A young man of 29, still unknown outside the quiet walls of Trinity College, Cambridge, has spent months in a darkened room with nothing but a feather, a prism, and a beam of sunlight, no thicker than a knitting needle. When he finally emerges, Blinking into the pale English daylight, he carries a letter that will detonate across Europe like cannon fire. His name is Isaac Newton, and he has just declared that light itself is made of tiny, invisible bullets. He does not yet call them photons. That word will wait 2.5 centuries. But the picture he paints is vivid and merciless. Light, he says, is a shower of corpuscles, minute material particles, flung out from the sun, from candles, from glowing coals, traveling in perfectly straight lines at a speed so colossal that it crosses the diameter of Earth's orbit in 7 or 8 minutes. These corpuscles are not all identical. Some are larger or heavier, some smaller or lighter, and that difference in bigness, as Newton sometimes calls it, determines their color. Red corpuscles are the largest and most stubborn. Violet are the smallest and most easily deflected. When the entire swarm strikes the eye, the mixture appears white. When it is sorted by a prism, the hidden rainbow spills out in silence. To understand why this idea seized Newton's imagination, and soon the imagination of the entire scientific world, we must step into that darkened chamber with him. Picture the scene: heavy woolen curtains drawn tight, a single round hole bored through the wooden shutter, a beam of raw sunlight stabbing across the room like a white-hot wire. Newton places a triangular block of glass in its path. On the opposite wall, instead of a clean white circle, there appears an oblong spectrum 5 times longer than it is wide crimson, melting into orange, green giving way to a blue, so pure it hurts to look at, and at the far end a violet that seems almost to hum. For the rest of his life, Newton will remember the shock of that first, elongated rainbow. No one had ever seen it quite so clearly before, because no one had taken such obsessive care to exclude every stray glimmer. He tries everything to make the colors change their nature. He sends the red alone through a second prism, still red. He blocks the blue and lets only yellow pass, still yellow, unspotted by any other hue. He catches the entire spread in a lens, focuses it, and sends it into another prism, turned upside down. The colors march back together and fuse once more into dazzling white. The conclusion is inescapable: white light is not simple or primordial, as Aristotle and Descartes had taught. It is a heterogeneous mixture, a mob of different particles, each carrying its own unalterable identity. Glass does not tint the light, it merely sorts the corpuscles the way a sieve sorts gravel. Newton does not stop at rainbows. He turns his attention to the thin films that produce the swirling colors in soap bubbles and in oil slicks on water. He presses a plano-convex lens with a long radius against a flat sheet of glass and watches rings of color bloom outward. From the point of contact, pale yellow, then vivid crimson, then green, then a second yellow brighter than the first. He measures the exact thickness at which each color appears and discovers that the sequence repeats every time the air film thickens by a precise interval. To explain this, he proposes that every corpuscle of light travel with alternating fits of easy reflection and easy transmission. When a corpuscle strikes a surface during a fit of easy reflection, it bounces. In a fit of easy transmission, it passes through. The fits alternate at regular distances, and when light reflected from the top and bottom of a thin film arrive at the eye together, sometimes the fits coincide and the colors intensified, sometimes they oppose and the colors destroyed. The mathematics is intricate, but the picture is pure mechanism, tiny bodies obeying simple rules like miniature planets. Across the channel, Robert Hooke, the irascible curator of experiments at the Royal Society, reads Newton's paper and explodes. Hooke has his own theory. Light is a very short, very fast vibration in the ether, like a pulse sent along a taut rope. To him, Newton's corpuscles are a regression to medieval crudity. A furious exchange of letters follows. Newton, thin-skinned and already retreating into secrecy, responds with icy precision, demolishing Hooke's objections point by point. When Hooke dies in 1703, Newton is elected president of the Royal Society and, according to legend, ensures that the only known portrait of his rival disappears forever. But the real triumph comes in 1704, when Newton finally publishes Optics, in English rather than Latin, so that artificers and mechanics can read it. The book is a masterpiece of experimental theater. Query after query at the end, 31 in the final edition, Planck'S, of doubt about the wave theory while never quite abandoning particles. Do not bodies act upon light at a distance, he asks, and by their action bend its rays. The language is deliberately ambiguous, but the weight of Newton's authority is absolute. For the next 100 years, almost no British natural philosopher dares to speak openly of waves. Yet the corpuscular theory is more than prestige. It feels right in the bones. We speak of light striking the eye, of a glare that hits us, of casting a beam. Soldiers fire muskets, cannon hurl iron balls, arrows fly. Why should light be different? When a mirror throws a spot of sunlight across a room, it behaves exactly like a projectile rebounding at equal angles. When a lens focuses the sun's rays to a point and ignites paper, concentration of heat feels like a gathering of tiny hot bullets. Even the newly discovered phenomenon of pressure exerted by light on a surface, observed by Pyotr Lebedev only in 1901, long after the theory's fall, would later seem to confirm the intuition. Only something with mass and momentum can push. Newton's corpuscles also solve an ancient riddle. Why does light cast such sharp shadows? Sound waves bend around corners and fill a room even when the door is only ajar. Water waves spread after passing through a narrow gap. But light seems to obey geometry with tyrannical strictness. A particle theory explains this effortlessly. Bullets fly straight unless something gets in the way. Waves should diffract, and in Newton's day, no one had seen clear evidence that they did. So complete is the victory that when a young French engineer named Étienne Louis Malus discovers in 1808 that light reflected from windows at a certain angle can be blocked by a second reflection just as if it had acquired a sidewaysness, he triumphantly announces the discovery of polarization as a property of corpuscles lined up like soldiers. The wave theory, he declares, is dead, and yet, in the quiet laboratories of Europe, tiny cracks are already forming. A Scottish physician named Thomas Young is about to perform an experiment so simple that a child could do it, and in doing so he will drive a stake through the heart of Newton's beautiful mechanical dream. But that is the next chapter. For now, the world belongs to the corpuscles. They march across lecture halls, gleam in the lenses of telescopes that discover new planets, sparkle in the chandeliers of Versailles. They are the emblem of a clockwork universe where everything, even the rainbow, can be reduced to little balls in motion. And at the center of it all stands the solitary, white-wigged figure of Newton, half scientist, half sorcerer, who has weighed light itself in his hand and found it made of atoms of fire. That is the spell the 19th century will have to break. And when it finally does, the sound will be heard around the world. The first crack appeared where Newton himself had left a door ajar. In the quiet queries at the end of optics he had asked, almost playfully, whether light rays might not excite vibration in the retina, or whether the warmth of sunlight might not be caused by the violent agitation of corpuscles. He never followed the thought, but others did. By the 1790s, a few lonely voices, most of them outside Britain, where Newton's ghost still walked the corridors of the Royal Society, began to whisper that light might be a wave after all. Then, in 1801, a 30-year-old English physician and polymath named Thomas Young stood up before the Royal Society and detonated a bomb no one saw coming. Young had noticed something odd while watching sunlight flicker through the slats of Venetian blinds. At the edges of each shadow there were delicate colored bands, far too regular to be accidents of dirt or imperfection. He suspected interference, the same phenomenon that makes organ pipes sing louder when two notes are slightly out of tune, or that creates the iridescent colors on a beetle's wing. To test it, he did something breathtakingly simple. He took a card, pierced it with a pin to create a single tiny source of light, then held a thin hair, later a narrow slit, in the beam. On a screen beyond, the shadow of the hair was not sharp-edged, as Newton's corpuscles demanded. Instead, it was fringed with bright and dark bands that marched outward in perfect symmetry. Next he used two hairs side by side, and the bands from each overlapped, sometimes reinforcing one another into brilliant light, sometimes canceling into darkness. Finally he replaced the hairs with two pinholes, or two razor-thin slits separated by less than a millimeters. The result was spectacular. Hundreds of alternating bright and dark lines, straight as ruled, stretching across the screen. Only waves could do this. Particles fired like musket balls would either pass through the slits or be blocked. They could never conspire to create such orderly annihilation and reinforcement. Young called it the principle, the interference of light. In a single evening he had resurrected Huygens' forgotten wave theory and dealt Newton's corpuscles a wound from which they would never recover. The Royal Society greeted his announcement with stunned silence, followed by outrage. One member rose to declare that Young had revived the exploded doctrine of Huygens and was guilty of destroying the authority of Newton. Young was mocked in the Edinburgh Review as a frivolous dilettante who dabbled in too many sciences. He retreated, wounded, and spent the next decade deciphering the Rosetta Stone instead. But the genie was out of the bottle. Across Europe, younger minds seized on his discovery. In France, a brilliant engineer named Augustin-Jean Fresnel, who had once been imprisoned for supporting the Royalists against Napoleon, read Young's papers in secret. Fresnel had been experimenting with diffraction himself. He noticed that when light passed the edge of a razor blade, the shadow was not clean. Inside the geometric shadow there were bright bands, and outside there were dark ones. Newton's theory could offer no explanation except vague inflection of corpuscles near the edge, an idea Newton himself had disliked. Fresnel, working alone in an attic with homemade apparatus, calculated what would happen if light were transverse waves, waves that vibrate perpendicular to their direction of travel, like a plucked violin string, rather than longitudinal pressure waves like sound. The mathematics was ferocious, but the results were miraculous. Fresnel's equations predicted exactly where every bright and dark fringe would fall in Young's double-slit experiment in the shadow of a razor, even in the intricate patterns produced by a tiny opaque disk. In 1818 he submitted a memoir to the French Academy entitled On the Diffraction of Light. A judging committee headed by Laplace, Poisson, and Arago, all believers in particles, set out to demolish the upstart. Poisson, a master of mathematical cruelty, derived a consequence of Fresnel's equations that he thought would prove them absurd. If a small circular obstacle were placed in a beam of light, Fresnel's theory predicted a bright spot at the very center of the shadow. Everyone knew shadows were dark. Poisson triumphantly announced the prediction as the death blow. Arago, more curious than vindictive, went to the laboratory and tried it. There, in the middle of the black disk's shadow, glowed a tiny, perfect point of light, today called the Arago spot or Poisson spot. The wave theory had passed the ultimate test. It predicted something no one had ever imagined, and the world obeyed. One by one, the remaining pillars of the corpuscular theory crumbled. In 1808 Malus had discovered polarization by reflection and declared it proof of corpuscles lined up like spinning rifle bullets. Fresnel and Young showed that polarization was exactly what transverse waves would do. Their vibrations could be forced into a single plane. In 1845, Michael Faraday discovered that a strong magnetic field could rotate the plane of polarization, proof that light was intimately connected to electromagnetism, not to mechanical projectiles. Then, in 1850, Léon Foucault and Hippolyte Fizeau performed the experiment that finally administered the coup de grâce. Newton had predicted that corpuscles would travel faster in water than in air because the attractive forces of the denser medium would accelerate them, just as a falling apple speeds up near the ground. Foucault and Fizeau sent pulses of light through long tubes of water and measured the speed with rotating mirrors. The result was unambiguous: light slows down in water. The corpuscular theory was finished. Newspapers across Europe carried the news like an obituary: Newton's emission theory overthrown. By the 1860s, when James Clerk Maxwell published his equation uniting electricity and magnetism, the identity of light was sealed. Light was an electromagnetic wave, a self-propagating dance of electric and magnetic field, needing no ether after all, though that realization would wait for Einstein. The speed c in Maxwell's equations was not just any speed, it was the speed of light, measured in vacuum to 7 decimal places. And so, almost exactly 2 centuries after Newton's prism had cast its elongated rainbow across a Cambridge wall, the corpuscular theory breathed its last. It had explained so much: straight lines, sharp shadows, reflection, refraction, even the pressure of light. It had felt inevitable, mechanical, modern. Yet it was wrong in almost every particular. Light is not made of particles shot from the sun, it is a vibration that carries the sun's message across the void without moving any matter at all. Newton himself, had he lived to see the end, might have taken a strange comfort. In the very last query of optics he had written, "If anyone should ask how a wave can be propagated without a medium, I would ask him in return how a corpuscle can be propagated without attracting or repelling others." He suspected, perhaps, that both pictures were too simple. When Einstein revived the particle idea in 1905 to explain the photoelectric effect, he did not bring back Newton's corpuscles. His photons have no size, no bigness, no trajectory altered by prisms in the Newtonian way. They are quanta, packets of wave energy that sometimes behave like particles when they are born or die. The wave does not disappear, it merely learns to wear a second face. The long reign of the corpuscular theory, then, was neither a mistake nor a detour. It was a necessary adolescence. Humanity had to believe, for 2 centuries, that light was something we could almost touch, little bullets of pure energy, before we were ready to accept the deeper, stranger truth, that light is a ghost, a disturbance. In Nothing, a song the universe sings to itself across empty space, and somewhere, in whatever afterlife awaits great scientists, Isaac Newton, who spent more time on alchemy and biblical chronology than on physics, might finally smile. After all, he was right about one thing that day in 1672. White light is not simple. It is a chorus of frequencies, a parliament of colors, a storm of waves pretending, when it must, to be particles. The rainbow he loved so much was always more subtle than even he dared dream. The year is 1678. In a small house on the Hofstraat in The Hague, a frail man of 49 sits hunched over sheets of paper covered with delicate diagrams of spheres and envelopes. His pendulums tick softly in the background, keeping time for the clocks that have made him famous. Outside, the Dutch winter presses against the windows, but inside, Christian Huygens is chasing something warmer and brighter. The secret of light itself? He has spent years watching waves, not the slow, heaving waves of the North Sea, but the quick, invisible ones that carry sound through air, the ripples that race across a pond when a swan takes flight, the silent tremors that travel along a taut string when one end is plucked. To Huygens, light feels like the fastest and finest of these disturbances, while Isaac Newton, still a young man across the water, is beginning to dream of corpuscles. Huygens is quietly writing one of the most beautiful books in the history of science, Traité de la Lumière. In it, he makes a claim so simple and so revolutionary that it will take the world almost a century and a half to believe him. Light is a wave, and it moves through an invisible, all-pervading ocean we call the luminiferous ether. Imagine, he writes, standing at the edge of a still lake at twilight. You drop a single pebble. A perfect circle of ripples spreads outward. Now drop a second pebble every second. A train of circles moves across the water, each new crest pushing the previous one farther. The water itself barely moves up and down, yet the disturbance races to the far shore. This, says Huygens, is how a candle lights a room hundreds of feet away without sending any substance across the gap. The flame shakes the ether next to it. The shaking passes from neighbor to neighbor, hand over hand, through the invisible medium, until it reaches your eye and makes the retina tremble in sympathy. But light does something sound and water waves cannot do. It trails in razor-straight lines and casts knife-sharp shadows. How can a wave refuse to bend around corners the way your voice fills a hallway? Huygens' answer is one of the most elegant ideas ever born in physics. He calls it his principle. Take any wave front. Imagine the crest of a ripple frozen in time, a curved line of disturbance. Every single point along that line, Huygens says, acts as if it were a new pebble, sending out tiny circular wavelets in all directions. After the briefest instant, the new wavefront is the envelope that just touches all those wavelets. Where the wavelets pile up in step, the light is bright. Where crest meets trough, darkness reigns. Draw the picture carefully, and you discover something astonishing. The envelope is almost perfectly flat and continues in exactly the same direction as the original wave. The wavelets, spreading sideways, cancel each other out, leaving only the forward march. Light goes straight, because millions of tiny interferences conspire to destroy every path except the straight one. With this single principle, Huygens derives, in a few pages, the complete laws of reflection and refraction. He shows why a mirror returns a ray at the same angle it arrived, why a spoon in a glass of water appears broken, why the setting sun is flattened into an oval. He even explains rainbows by showing how sunlight bounces once inside spherical raindrops and emerges concentrated at 42 degrees. All of it flows from geometry, so pure it feels like listening to Bach. Yet Huygens does not stop at ordinary glass and water. In 1669, a Danish sea captain had sent him a strange crystal from Iceland. All places, Iceland. A transparent rhomb of calcite that split every beam of light into two. Look through it at a pinhole, and you see two images dancing side by side. Newton had tried to explain this double refraction with corpuscles of different shapes, but his theory grew tortured and ugly. Huygens places the crystal on his desk, lets sunlight fall through it onto a sheet of paper, and watches the two beams separate. Then he does something almost no one had tried. He rotates the crystal. One beam stays fixed, the other circles around it like a moon. He realizes that inside the crystal the wave front is no longer spherical. In most directions the wavelets spread as perfect spheres, but along the crystal's optic axis they stretch into ellipsoids. The mathematics is delicate. He has to invent new coordinate geometry on the spot, but when the calculations are finished the paths of both rays fall out exactly as measured. Huygens has explained a phenomenon that defeated Newton with a single, graceful stroke. For the first time in history, a wave theory has beaten the particle theory on its own ground. He ends the traité with a quiet prophecy. If light is a wave, then someday we should be able to make two beams interfere, strengthen, or cancel each other, the way sound waves do when two flutes play slightly out of tune. He even sketches an experiment. Send sunlight through two tiny holes close together and look for bright and dark bands on a screen. He never performs it himself. His eyes are failing, his health fragile, but the drawing, the picture is enough. The seed is planted. When the book appears in 1690, the reaction is polite but cool. In France, the followers of Descartes prefer their own vortex theory. In England, Newton's star is rising fast, and his corpuscles feel more solid, more English, more in tune with the new mechanical philosophy. Huygens dies in 1695, almost forgotten, clutching a manuscript on the rings of Saturn. His wave theory slips into obscurity, kept alive only by a handful of mathematicians who admire the beauty of his diagrams. For more than a century the world chooses Newton's bullets over Huygens' ripples. The ether is dismissed as an unnecessary ghost. After all, cannonballs fly through empty space without needing jelly to push them along. Huygens' exquisite principle gathers dust on library shelves while generations of students learn that light consists of particles too small to imagine, streaming from the sun like golden grapeshot. Yet the picture Huygens painted is too lovely to stay buried forever. In the attic laboratories of the early 19th century, lonely experimenters will rediscover his book, blow the dust from its pages, and realize that the Dutch clockmaker's son saw farther than the man who weighed the moon. When Thomas Young stands up in 1801 and shows the Royal Society his interference fringes, he will not claim to have invented the wave theory. He will simply say, with characteristic modesty, that he is reviving the beautiful theory of Huygens. And when the fringes appear, hundreds of bright and dark lines exact where Huygens' secondary wavelets predicted, the scientific world will gasp, because it will suddenly recognize the voice of a man speaking across 120 silent years. That is the tragedy and the glory of Christian Huygens. He built a palace of light so perfect that the world was not ready to live in it. He died believing his life's greatest work had failed. He could not know that the ripples he sent out in 1678 would one day become the mightiest wave in physics, sweeping away Newton's empire and carrying us all the way to Maxwell, Einstein, and the quantum sea beyond. In the end, the quiet Dutchman who loved clocks and pendulums understood time better than anyone suspected. His wave was merely waiting for the right moment to break upon the shore. The exile lasted exactly 111 years, from the death of Huygens in 1695 until the evening of Thursday, 12 November 1801. The wave theory of light was little more than a footnote, a curiosity for scholars who liked elegant mathematics but had no experiments to back it up. In lecture halls from Edinburgh to Naples, professors drew little circles on blackboards representing Newton's corpuscles bouncing off mirrors, and students nodded as though the matter were settled forever. The ether, that ghostly ocean Huygens had needed to carry his ripples, was laughed out of polite conversation. Nature abhors a vacuum, the Newtonians said, but she abhors invisible jelly even more. Then, on that November night in London, a soft-spoken Quaker physician named Thomas Young rose to address the Royal Society. He was 28, already famous for having helped decipher the Rosetta Stone, and notorious for the breadth of his curiosity that made older men call him Phenomena Young behind his back. He began quietly, almost apologetically, saying that he wished merely to draw attention to an old theory, once thought exploded but perhaps deserving of revival. He laid a single sheet of paper on the table. On it was a drawing Huygens himself might have recognized, two tiny pinholes side by side, a beam of sunlight passing through them, and on a distant screen a pattern of bright and dark bands. Young had made the experiment himself, in a darkened room in Welbeck Street, using nothing more than a candle, a visiting card pierced with a needle, and a steady hand. Where the two beams overlapped, light did not simply add together as bullets would. Instead it brightened and dimmed in perfect alternation, exactly as though one set of waves were climbing the crests of the other and then sliding into the troughs. When he moved one pinhole a fraction closer to the other, the entire pattern shifted, the way ripples from two pebbles change when you alter the distance between drops. He called the phenomenon interference of light, and in a single stroke he resurrected Huygens from the dead. The reaction was volcanic. Henry Brougham, writing anonymously in the Edinburgh Review, tore into Young with a venom that still shocks. Today we now dismiss, with the unceremonious brevity which it deserves, a work spreading into two huge quartos, breathing nothing but nonsense from beginning to end. The reviewer, later revealed as Brougham himself, declared that Young had attempted to overthrow the labors of a whole life spent by Newton. Young's crime was not error, it was lèse-majesté against the god of English science. For several years Young retreated stung. He published no more on light, turning instead to life insurance tables and Egyptian grammar. But the fringes would not go away. Every time someone repeated the experiment in a quiet room, the same silent stripe appeared, mocking the corpuscular theory with their impossible precision. In France, a young civil engineer named Augustin Jean Fresnel, exiled to a rural tax office for having backed the wrong side in Napoleon's 100 Days, read Young's papers by candlelight. Fresnel had never heard of Huygens' principle until he rediscovered it for himself while watching sunlight diffract around a hair. He wrote to Young in careful English, addressing him as the restorer of the wave theory. Together, though they never met, they began the campaign that would finally break Newton's empire. Fresnel took Huygens' secondary wavelets and made them sing. He showed that if the wavelets were allowed to interfere with one another everywhere in space, not just along the forward envelope, then every optical phenomenon fell into place with mathematical inevitability. Diffraction, which Newton had explained away with vague inflection, became a triumph. Light bending around a straight edge produced exactly the pattern Fresnel calculated to 6 decimal places when he predicted the bright spot in the center of a circular shadow, and Dominique Arago confirmed it in the laboratory. The last doubters fell silent. By 1821, even the French Academy, once the fortress of corpuscular faith, awarded Fresnel its grand prize for optics. The citation praised the beautiful theory of Huygens revived and perfected by Young and Fresnel. The wave had returned, and this time it came with armies of equations and experiments no one could dismiss. The final coronation came in the 1860s when a shy Scottish theorist named James Clerk Maxwell sat in a quiet room in Glenlair and asked a simple question: what happens if electricity and magnetism are not separate forces, but two faces of one thing? When he finished writing down the equations that now bear his name, a single number fell out: the speed at which an electromagnetic disturbance would propagate through empty space. He looked up the best measurement of the speed of light, made only a few years earlier by Fizeau and Foucault. The numbers matched to every digit he could measure. Light, Maxwell realized, was not a wave in some mysterious ether. Light was the wave, an oscillating electric field giving birth to a magnetic field, which in turn gave birth to another electric field, the two dancing together across the void at 290,792 kilometers per second. No medium was needed. Any more than a rumor needs a carrier pigeon, the fields sustained themselves. Huygens had been right about the wave, but even he could not have imagined how pure and self-sufficient the wave would turn out to be. In 1887, in a dusty attic laboratory in Karlsruhe, Heinrich Hertz set out to test Maxwell's prediction. He built a spark gap transmitter and a simple loop receiver. When the spark jumped, a tiny answering spark leapt across the loop, 30 meters away. Even when he placed thick walls between them. He called them electric waves, but everyone else immediately recognized them as light in slow motion, radio waves, invisible cousins of the colors we see. The entire spectrum, from gamma rays to long-wave radio, was suddenly one family, all traveling at the same sacred speed c, all obeying Huygens' principle in their own way. The corpuscular theory was not merely defeated, it was erased. Textbooks were rewritten overnight. The ether, which had been brought back to carry light waves, was quietly retired again after Michelson and Morley failed to detect any wind from Earth's motion through it. By 1900 the wave reigned supreme, serene and unchallenged. And yet, in the glow of 1,000 heated filaments, in the strange behavior of ultraviolet light kicking electrons out of metals, new shadows were gathering. The wave, for all its majesty, could not explain everything. In the blackbody ovens of Berlin laboratories, the gentle curve of radiation refused to match Maxwell's equation. A desperate Prussian physicist named Max Planck would soon be forced to assume that the wave sometimes delivered its energy in discrete packets, as if, after all, it carried tiny bullets inside it. But that is another story. For now, let the record stand. Christian Huygens, the lonely clockmaker, who died believing his greatest work had failed, was right. Light is a wave. It travels as a shiver through nothing at all, a pure disturbance that needs no substance to sustain it. Every photon that reaches your eye tonight from the Andromeda galaxy began its journey 2.5 million years ago as part of a wavefront that has crossed the emptiness without ever losing its shape. Guided by the same principle Huygens sketched with quill and ink in a lifetime before Newton published his optics. Somewhere, in the silence between heartbeats, you can almost hear the soft Dutch voice whispering. Across the centuries, every point on a wavefront becomes a new source of wavelet, and the universe, obedient as ever, answers with rainbows, with radio songs, with the silent roar of starlight that has traveled since the dawn of time to find us. The wave has come home. In the dim candlelight of a London attic in the summer of 1801, a young physician named Thomas Young stood alone before a simple apparatus that would change everything. A beam of sunlight, a visiting card pierced by 2 needle-thin slits, and a white screen a few feet away. When he let the light pass, the wall did not glow with 2 overlapping patches of brightness, as Newton's particles demanded. Instead, it exploded into hundreds of delicate stripes, bright, dark, marching across the surface like the teeth of a comb made of pure light. Young had just performed the most dangerous experiment in the history of optics. He had forced light to testify against itself, and the verdict was unmistakable. Light is a wave. For over a century Newton's corpuscles had ruled unchallenged. Bullets of light explained sharp shadows, straight rays, the burning glass that could set paper alight. Yet here, in this quiet room, light was doing something no bullet could ever do. It was destroying itself. Where the 2 beams crossed, darkness sometimes reigned even though light was pouring in from both slits. Crest met trough and cancelled and vanished. Only waves can commit suicide in this way. Young called the phenomenon interference, and in a single evening he resurrected Huygens' buried dream. He showed that the distance between the bright fringes depended exactly on the wavelength of each color. Red fringes wider, violet tighter, just as ocean swells from distant storms space themselves farther apart than the ripples from a dropped pebble. He measured the wavelengths for the first time. Red light about 1/35,000th of an inch, violet half that. Suddenly the entire rainbow had a scale. The Royal Society greeted his discovery with fury. Anonymous reviewers called him a charlatan trying to overthrow Newton, but Young had opened a door no one could close. Across the channel, Augustin Fresnel read the forbidden papers and turned interference into a weapon. He flooded Paris with calculations showing that every shadow, every glint on water, every colored ring in a soap bubble was an interference pattern written by invisible waves wrestling in the air. By 1818, the French Academy could no longer deny it. When Poisson predicted, hoping to mock, that a wave theory must place a bright spot in the very center of a circular shadow, and Arago found the spot glowing exactly where calculation said it would, the last fortress fell. Light had spoken, and it spoke in waves. The double-slit experiment today performed by schoolchildren with a laser pointer and a hair remains the most profound demonstration in all of physics. It is the moment the universe admits. It is made of vibrations, not substances, of dancing fields, not flying atoms. 2 centuries later, when we send single photons through those same slits and still see the stripe build up one dot at a time, we are watching the ghost of Thomas Young smile in the dark. He never sought fame. He published little, quarreled less, and died young. Yet every screen that glows, every rainbow that arches, every star that twinkles is quietly singing the song he first heard that summer night in London. Light is a wave, and the world is its instrument. In a narrow Paris apartment in 1850, a 27-year-old engineer recently released from prison for royalist sympathies sat surrounded by cardboard screens, sewing needles, and scraps of mirror, and a single candle. His name was Augustin Jean Fresnel, and he was about to do something no one had thought possible: explain why light has sides. Everyone knew that light reflected from water or glass at certain angles became strangely choosy. Hold a crystal of Iceland spar over a page, and the words split in one beam twisted left or right when you turned the crystal, while the other beam stayed calm. Sailors had noticed that glare from the sea vanished when they looked through a tilted pane of glass. In 1808, a French officer named Etienne Louis Malus had called this selective blindness polarization after the poles of magnetism, and Newton's followers rejoiced. Only spinning corpuscles lined up like tiny magnets could behave this way. Fresnel, working in secret because Bonaparte's police still watched him, suspected the truth was simpler and stranger. Light, he believed, was already a transverse wave, like a wave traveling along a skipping rope, vibrating up and down or side to side, not a compression wave like sound. If the vibrations were forced into one plane, the light would refuse to vibrate in the perpendicular direction, and certain reflections, or crystals, could act like gates that only let one orientation pass. He built his proof with heartbreaking ingenuity. He took 2 mirrors tilted at exact angles and reflected a single beam so that the 2 paths crossed again. Where they overlapped, he saw the familiar interference fringes, proof the beams were waves, but when he slipped a thin slice of mica between them, the fringes vanished in one direction and reappeared in the other. The light had acquired a direction of vibration, and the mica had stripped away the perpendicular component. He then carved delicate plates of glass into staircases only a few wavelengths thick, and watched colors bloom and die as the 2 polarizations raced each other, arriving sometimes in step, sometimes opposed. In 1818, he sent his memoir to the French Academy. The old Garde Laplace, Biot, Poisson still worshipped Newton's particles. They set a prize topic on diffraction, certain no wave theory could survive the test. Fresnel entered anyway, filling hundreds of pages with integrals that described every curl of light around a razor's edge. When the envelopes arrived from the contestants were opened, the judges stared in silence. Fresnel's equations matched reality to the width of a hair. The final blow came in 1821. Fresnel placed 2 prisms together to create what we now call a Fresnel rhomb. A single beam entered ordinary light and emerged perfectly circularly polarized, vibrating in a corkscrew. No arrangement of spinning bullets could ever do that. The hall erupted in applause. Even Arago, once a skeptic, stood and declared the wave theory victorious. Fresnel never lived to see the full triumph. Tuberculosis took him at 39, but before he died he whispered to his brother, "I have never been so happy." He had given light its hidden dimension. Every pair of sunglasses, every LCD screen, every 3D movie today owes its existence to the fevered nights of that young exile who proved that light does not merely travel, it dances and twirls like a ribbon in the wind. Polarization was the signature no particle could forge. The wave had spoken in a voice no one could mistake. In a quiet farmhouse in the Scottish countryside, far from the noise of London and the intrigues of Paris, a shy, red-bearded mathematician named James Clerk Maxwell spent the winters of 1861 to 1864 alone with paper, ink, and a burning question: what if electricity and magnetism were not two separate forces, but two faces of the same thing? He began with the known laws, Faraday's lines of force, Ampere's currents, Gauss's beautiful symmetries, and slowly, almost reverently, wrote down 4 equations that tied them together. They looked innocent enough, 20 lines in all, but when he combined them, something miraculous happened. A wave equation fell out, describing a disturbance that would travel through empty space at a speed he could calculate from purely electrical and magnetic measurements. He reached for the latest tables, 310,740,000 meters per second. Then he looked up the best value for the speed of light, measured by Fizeau only. A few years earlier, 314 million meters per second. The numbers were the same within experimental error. Maxwell stared at the page for a long time. Then he wrote in his notebook, almost whispering, "This velocity is so nearly that of light that it seems we have strong reason to conclude that light itself, including radiant heat and other radiations, if any, is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field according to electromagnetic laws." In that moment, in the cold Scottish dusk, light lost its mystery and gained an identity. It was no longer a stream of corpuscles, no longer a ripple in some invisible jelly called ether. Light was electricity and magnetism dancing together, each creating the other as they ran. An oscillating electric field gives birth to a magnetic field at right angles. The changing magnetic field recreates the electric field ahead of it, and the pair leapfrog across the void forever, needing nothing but themselves to exist. Red light vibrates 430 trillion times a second, violet 770 trillion, yet all travel at the same sacred speed. See the heartbeat of the universe. Maxwell never saw his waves. He died in 1879, still young, believing his theory beautiful but unproven. 8 years later, in a dark attic in Karlsruhe, a 29-year-old German named Heinrich Hertz built a spark transmitter and watched tiny answering sparks leap across a gap 30 meters away. He varied the size of his apparatus and measured wavelengths from meters down to centimeters. Every prediction, reflection, refraction, polarization, interference obeyed the same laws as visible light. Hertz wrote simply, "It is impossible to avoid the conclusion that light, heat radiation, and electromagnetic waves are identical in nature." The entire spectrum suddenly became one family: radio waves, microwaves, infrared, the narrow rainbow. We call visible, ultraviolet, X-rays, gamma rays, all the same phenomenon, only the frequency changing. Sunlight was revealed as a faint hiss of radiostatic accompanying the colors we see. The stars were whispering to us in voices that stretched from kilometers to trillionths of a meter. Maxwell's equations did more than identify light. They crowned the wave theory with absolute victory. No mechanical model, no ether, no corpuscles could ever match their austere perfection. Light was pure field, pure geometry, pure music written in electric and magnetic ink across the emptiness between galaxies. Today, every antenna, every laser, every Wi-Fi router sings the song Maxwell first heard in silence. And when we, bathed from birth in invisible oceans of electromagnetic waves, are living proof that a solitary Scot, scribbling by lamplight in a farmhouse no one remembers, once caught the universe in 4 lines and saw that it was light. By the 1890s, the wave theory stood triumphant, almost arrogant in its perfection. Maxwell's equations explained every color, every shadow, every glint on water. Light was an electromagnetic wave, pure and continuous, sweeping across the cosmos like an endless symphony. Yet in the quiet laboratories of Berlin and Vienna, where physicists study the soft glow of kiln-hot metal, something refused to obey the score. A closed oven, heated to a dull red, radiates a gentle curve of energy, more infrared than visible, peaking gently, then fading toward ultraviolet. Classical wave theory, armed with Maxwell and Boltzmann, predicted disaster. Energy should pour without limit into the shortest wavelengths. The glow should explode into infinite brilliance at the ultraviolet end and beyond. Physicists called it, half in jest, the ultraviolet catastrophe. A room temperature brick, by rights, ought to blind you with X-rays the moment you switched on a lamp. Reality, mercifully, was tamer. Another ghost haunted the ether. If light waves needed a medium, Earth should feel a wind, as it hurtled through the luminiferous ether at 30 kilometers per second. In 1887, on a stone pier in Cleveland, Ohio, Albert Michelson and Edward Morley split a beam of light, sent the halves racing along perpendicular arms, then brought them back together. If the ether existed, one half should lag, producing shifting fringes. The mirror floated on Mercury, the apparatus sealed against the slightest tremor. They measured and measured again, through day and night, through seasons. The fringes never moved. The ether wind was exactly zero. The medium through which all light supposedly traveled was nowhere to be found. These two quiet failures, one in glowing cavities, one in a silent basement, were the first cracks in the classical heaven. The wave rained, but it rained over a kingdom with locked doors it could not open. In 1900, on a cold October evening, Max Planck stood before the German Physical Society and offered a desperate fix. To make the oven curve match experiment, he assumed, reluctantly, almost ashamedly, that energy was not poured smoothly like water but handed out in tiny, indivisible coins. He called them quanta. The size of each coin was proportional to the frequency of the light. E equal to hn nu, a formula he scribbled almost as a bookkeeping trick. He expected the idea to vanish once a better classical explanation appeared. It did not vanish, but only from classical physics forever. 5 years later, Einstein took Planck's ugly duckling and declared it a swan. Ultraviolet light kicking electrons from metal, the photoelectric effect, behaved as if light arrived in discrete bullets, not continuous waves. The bullets carried exactly the energy Ah and U, and if they were too weak, no electrons escaped, no matter how bright the beam. Light, the purest wave humanity had ever known, was secretly carrying particles inside it. The ether received its own death certificate in 1905 when Einstein's special relativity showed that the speed of light is the same for every observer, with no need for any medium at all. The wave no longer swam, it simply was. By the 1920s, the double-slit experiment, once the decisive proof of waves, began produce single flashes on photographic plates when light was dimmed to one photon at a time. Yet the flashes slowly built the same interference stripes. Light traveled as a wave, arrived as a particle, and refused to choose. The pre-Planck era ended not with trumpets but with whispers, a missing ether whined, a too gentle glow from hot iron, a few stubborn electrons. The anomalies were small, almost polite, yet they tore the classical sky in two. Through the tear stepped the quantum century, where light is both wave and particle, where certainty dissolves into probability, and where the rainbow we have chased since ancient Greece finally reveals its last secret. It was never made of fire rays, nor corpuscles, nor even pure wave, but of something stranger still, something that is and is not until the moment we look. The untold story before Planck is the story of humanity learning, again and again, that the universe is far more subtle than our brightest dreams, and in that humility lies its deepest beauty.